Howdy, this is the Amateur Logician, and we're going to think about solving a 2x2 system of linear equations. We're going to solve it through pure substitution, so to speak. We're going to compare the solution to a determinant and to Cramer's rule. So let's say we have the linear equation ax plus by is equal to c, and linear equation dx plus ey is equal to f. So if we think of these two equations graphically on the Cartesian coordinate plane, there are three possibilities. So the first possibility on the xy plane is that the first equation and the second equation intersect at one point. So let's say the first equation is L sub 1, the second equation L sub 2. So here's L sub 1, here's L sub 2, and they meet at this important point. There's one solution. Another possibility is that there are no solutions where L sub 1 and L sub 2 are parallel and they have different y-intercepts. So there are zero solutions in that case. And the third possibility is that line 1 and line 2 are the same exact line, and so there are infinitely many solutions. So let's solve that system. We want to find out what x and y are going to be to satisfy both equations simultaneously. So we have, once again, ax plus by is equal to c, and dx plus ey is equal to f. So for example, from the first equation, let's just solve for x. So we have ax is equal to negative by plus c. Divide by a, so x is equal to negative by plus c over a. And then we will, so to speak, throw that into the second equation, and that will allow us to figure out what y has to be. So we have d times x, and x happens to be negative by plus c over a. We just substitute that in. Then plus ey is equal to f. So let's work on this. And I'm going to use the commutative rule to move things around a little bit through this process to make it a little bit clearer. So we have d times negative by. That's the same thing as negative b dy. And then we'll say plus cd over a plus ey is equal to f. If we want to add, we have to have the same common denominator. So we can get negative b dy plus cd over a plus aey over a. So we multiply the numerator and the denominator by a. So now we have common denominators. We can add that without a problem. I'm going to use the commutative rule to put aey first. Then our minus b dy plus cd over a is equal to f. Let's multiply both sides of the equation by a. So then we get aey minus b dy plus cd equals af. Let's isolate that y. So let's subtract cd from both sides of the equation to get aey minus b dy is equal to af minus cd. We want to solve for y, but we can factor that y out on the left-hand side. So y times the quantity, ae minus bd, and that equals af minus cd. So therefore, y is equal to, we'll just divide both sides of the equation by ae minus bd. So y is equal to af minus cd over ae minus bd. Great. So that is y. So to figure out x, we can just throw that, for example, into the first equation. So we have ax plus by is equal to c. So we'll just substitute that y in. So ax plus b times the quantity, af minus cd, over ae minus bd is equal to c. Let's multiply that out. So ax plus, so b times af, that's the same thing as abf. b times that negative cd is the same thing as negative bcd over ae minus bd equals c. We want that x by itself, so we might as well subtract this expression from both sides of the equation. So we get AX is equal to C minus ABF minus BCD over AE minus BD. Again, we want a common denominator, so we better deal with that fraction there. So AX is equal to, well, we'll just times C on the numerator and the denominator by that AE minus BD. So we get ACE minus BCD. I'm using the commutative rule. So it's C times the quantity AE minus BD. So we get ACE minus BCD over AE minus BD. Then our minus ABF minus BCD over AE minus BD. So we get AX is equal to ACE minus BCD minus ABF minus a minus, so plus BCD over AE minus BD. Let's simplify. So here's a negative BCD. Here's a positive, so those go away. So we get AX is equal to ACE minus ABF over AE minus BD. We want to solve for that x, so we'll just multiply both sides of the equation by 1 over a. So we get x is equal to, well, look at that right-hand side. So here's an ACE minus ABF. We can factor out that a. So in other words, we can get a times the quantity CE minus BF over AE minus BD. That's times 1 over a. So notice we have this a over here on the numerator and on the denominator. Those go away. So therefore, x is equal to CE minus BF over AE minus BD. Great. So we have our x, we have our y. This is the solution to any 2x2 system of linear equations. But notice a few cool things. So one of the interesting things that if you look very closely, you will notice that for x, the denominator is AE minus BD. But the same thing, it turns out, is true for y. We have this on the denominator, AE minus BD. And that's really the determinant of our system. So if we think about our system, we have x plus, let me try that again. We have AX plus BY is equal to C. We have DX plus EY is equal to F. So that is our 2x2 system of linear equations. If we think about the determinant of A, B, D, E, that's going to equal, if you know matrix algebra, AE minus BD. So the determinant of this here, in fact, is the denominator of both what y has to equal and what x has to equal, which is pretty interesting. But also we can compare this, for example, to Cramer's rule. That's one way we can solve a system of equations. So it would tell us that x is equal to the determinant of C, B, F, E over the determinant of A, B, D, E, and then y is equal to the determinant of A, C, D, F over the determinant of A, B, D, E. And if you do the math on that, you'll figure out that x is CE minus BF over AE minus BD, that's x. And then y is AF minus CD over AE minus BD. And that, of course, is consistent with what we found out when we're doing the pure substitution technique to solve any general 2x2 system of linear equations. So this process uses a lot of algebra, a lot of algebraic technique goes about in solving this type of problem. But But it's also very cool because we can pick up on the general pattern of what any 2 by 2 system of linear equations is. We can figure out, well, what is x and what is y to satisfy both equations. Now, to be sure, sometimes that system may be inconsistent, such that we get zero solutions. That happens. But it's also possible that we have infinitely many solutions as well. I hope this video has been interesting and helpful to you. Good luck to you, and be well.